close. He has been working for some time on a project called GHCJS, which is a backend for GHC that outputs JavaScript. So it's a surprisingly complete project. Almost any thing that you can write in pure Haskell, you can run in the browser. It's still a work in progress, but the performance is pretty good. I've checked it out myself. I was very impressed. If you're at all interested in using something other than JavaScript to write a front end for a web application, I would strongly suggest you take a look at GHCJS. He is in from the Netherlands, Utrecht, which I'm sure many of you have heard of. It's a school that does a lot of stuff with Haskell. Let's see, the project is also being worked on by a couple of other people. It's got, who's it? Does anyone know the other? Hamish, right? Yeah. And so it's been in progress for about a year and a half, right?
I think it's been in progress for longer. I have some problem setting this up.
If you give it a second, it usually figures it out. Just if you fiddle with it, it'll get angry.
Okay, well, so I did not start the project myself, indeed. I think the first author was Viktor Nazarov from Russia, who made basically proof of concept implementation. And Hamish Mackenzie from New Zealand took over when Viktor didn't have much time anymore, because Hamish was working on the Lexa IDE and he thought that.
You speak a little louder?
Louder?
Yeah. Who's louder?
This microphone. Yes,
I have a microphone. It sounds pretty loud to me here. But
just keep going. I'll fiddle with it.
Okay. And I took over because I'm interested in not having to use JavaScript as my.
Yeah, that's good. You figured out what the set dial was. Good. Keep going.
Test. Yeah. Okay, good. Better?
Yeah.
Okay. And just under a year ago, we basically concluded that our approach until then was somewhat back-end. Our performance was not good enough, and we were running into some trouble with things that we couldn't support. So I basically rebooted the whole project and we wrote the code generator from scratch. And well, the first part of that is now almost done, almost ready to be released when GHC 7.8 is out. And that's the part I'm going to talk about today. So, like I said, it's based on GHC 7.8. We could have tried to make it compatible with all the GHC, but as we will see later, we have to make some compromises that I'm not really very happy about. And anyway, at least now GHC is just around the corner. So, GHCJS is a standalone program. It's not merged into GHC itself. It's still way too experimental for that. We did actually, needed some changes in the GHC code base itself. We have some, JavaScript is a very different platform than what GHC is actually written for. For a function interface for Haskell, GHC is basically just for calling C. And even if you do Ruby or whatever or other high-level languages, you probably have to pass through the really low-level C layer, or you have to jump through some hoops. Well, one of the things that was changed recently in GHC is that we have some extension of the GHC API, which is the API that you get when you use GHC as a package, as a library from Haskell. So that we can support customizations to the foreign function interface, that we can hook our JavaScript code generator in the GHC pipeline in a much nicer way than we could before. And also GHC 7.8 has much improved support for cross-compilation. And GHCJS is basically a cross-compiler. We'll see later how exactly it works, but it sounds good. For that, GHC 7.8 also makes a huge difference. So I'm happy to be able to say that everything that we need is in. So in a few weeks, the GHC 7.8 is out, and we will probably, get everything done in time, be able to install GHCJS from hackers, which just about install GHCJS. The first half of the talk, I want to try to first show a few examples and talk about internals of GHCJS, what kind of code is generated, and why we've made certain choices. The second half, I hope to show a bit more of how GHCJS is used and how it fits in the Haskell ecosystem, like, for example, using Inline, what problems still have to be solved in that thing. Point 3, first slide. GHCJS uses GHC as a front end, so GHC does the type checking for us, which means we get for free all the Haskell extensions that GHC implements. And we don't have to do any work for that at all. So that's a really nice advantage of using GHC. For example, Faye does not have. We also get all the optimization, which can make a huge difference. If you have, for example, the vector package, all the stream fusion things that make a huge difference for certain packages. Those are available for us, and we get intermediate code that has all these important optimizations already done for us. We also have template Haskell support, which means that a much larger part of packages is usable with GHCJS, and we have a Cabal compiler flavor, which means you can, if you run Cabal install, you just add --GHCJS and it will install the package with GHCJS instead of GHC. And it will probably build most packages from package correctly without any changes, at least as long as they don't require any foreign dependencies. So C libraries, you probably have to do some work. I'll come to that in the second part. But if it's pure Haskell code, chances are pretty big that they work, and if they don't, you probably should file a bug report, because then there's something messed up. Most Haskell things should work, and what doesn't is pretty minor. And one of the new things that I just briefly mentioned is that we have a JavaScript FFI. If you know Faye or GHCJS, you know that they have some special parent syntax where you can write JavaScript code inline, which gets spliced directly into your functions, where you have some placeholders for your Haskell arguments and you can return things from JavaScript to Haskell. We have that now too in GHCJS. That's one of the extensions that's available in GHC 7.8. But it's, well, without GHCJS it's kind of useless, but it's really great. So, this talk I'm going to talk about the concurrent runtime, which is basically the whole, the most complete Haskell support we have. Before I started working on this new version, we had two code generators in GHCJS. One was, well, they had a bit bad names. One is the concurrent runtime and one was the non-concurrent runtime. The non-concurrent runtime has some advantages in code size, but it has some limitations. Many things are not supported by it. So for the making sure that I had everything ready for GHC 7.8, I decided to port the concurrent runtime first, and the non-concurrent runtime for people coming from Faye, for example, and who maybe just want to port some library or call into Haskell, get some result back instead of having all the threading and all the things like STM or ACIO exceptions. I'll explain all that in a moment. They can have a bit smaller code size. And, for some people that might maybe very trade-off. That's not quite ready, but I expect it to be ready in a few weeks. There is also some other project going on by Hamish McKenzie, mostly, which is WebKit, GTK, and JavaScript core bindings. The idea of those bindings is that they have the whole DOM API, the document object model from JavaScript that you can use to manipulate HTML documents in the browser. The idea is that WebKit GTK is one of the backends for the DOM bindings. And the package can be compiled with GHCJS, which means you get Haskell, just a DOM binding library in the browser. That's like you'd expect. But you can also compile the same library without changing any code to native code with the regular GHC. which means you can make a cross-platform application, one that really runs as a website and one that uses a WebKit GTK browser frame or an Android browser frame or something like that. So you still use the browser as the user interface, so you have the same widgets, the same code, but you have the actual Haskell code running natively for a bit more performance. So that's an interesting thing in the GHCJS ecosystem, also not quite in the scope of this. So the concurrent runtime is what I'm talking about today, and it's a pretty complete Haskell runtime. The goal is not to run every Haskell where possible, but the goal is at least to make most of Hackett usable with the compiler. And the advantage, at least for me, is that it's real Haskell. I like Haskell and I don't like being limited to some particular subset or not being able to use many of the great packages that are already available in package. For me as a compiler writer, it's a great advantage because I have millions of lines. Maybe that's a bit of an overstatement. At least a huge number of lines of code available from Hackett that I can run through the compiler, and I've already done lots of this. And if it works, then it just asserts that the compiler is at least able to do lots of prediction code and generate the correct results. So, well, we have preemptive threads. Fork.io works lightweight, they're emulated in JavaScript, but it's similar to how the single-threaded GHC runtime works. So we have one worker that does all the Haskell reductions and switches all the Haskell Fork.io lightweight threads internally. In JavaScript, we have to integrate that into the browser environment. So we have to do a bit of work in places to make that fit nicely. We'll come to that later. We have STM. Since when you have preemptive threading, it's actually not that hard to implement STM. As far as I know, GHCJS is the only implementation of the Haskell STM that actually has no bugs that I know of. I was working with Ryan Yates on the implementation and checking all the semantics, and we found some bugs in the GHC STM and did the correct thing. They had to do with invariants. They're fairly frequently used feature of STM. But well, the good news is that I can say that GHCJS does it correctly, and GHC will probably get it right soon to do it correctly too. Also, we have tail call optimization. JavaScript doesn't do that. There is in the ECMAScript 6 proposal a section that hasn't been worked on for at least a year or something. That is, yeah, well, the plan is to add it, but I have no idea when they're going to do it. So with Haskell, you pretty much assume that tail call optimization is going to work. And many algorithms will just fail if you don't optimize tail calls away. And JavaScript stacks are also, in general, much smaller than what you're used to from Haskell stacks. So I think that's a good thing to do. This is I'm talking now about a concurrent runtime, which is full tail call optimization and does not use the JavaScript stack for any calls at all. Our non-concurrent runtime still does full tail call optimization, but it uses the JavaScript stack for non-tail calls. So you're a bit more limited in the recursion depth that you can go with non-tail calls, but at least tail calls are optimized out. Also, for the type support, GHC has lots of primitive types, 64-bit, 32-bit, and the arbitrary precision integer. All of these are supported. And we use JavaScript libraries to do the actual operations for those. Integer is supported through JSBN. And, well, I have to say, there are not really terribly great arbitrary precision integer libraries for JavaScript, or actually any proper data structure libraries for JavaScript at all. So if you do something with large integers or something, expect to get a fairly big performance hit compared to GHC running on native code. Many other Haskell code runs fairly fast. But we have all the built-in primitive types. We even have pointers. And if you have foreign functions that uses pointers, you can implement implement the necessary JavaScript code to make that work. These all use typed arrays under the hood, and well, they work reasonably well. it's not that hard to make a package with small foreign C dependencies correctly in JavaScript. Let's see an example of that in the second part. Also, a unique thing of the concurrent runtime is lazy I/O. For example, loading some data from the server, lazy byte string or whatever it is. I'm not sure how much is already implemented, but it's pretty straightforward to edit. You can have some lazy huge byte string, for example, if that is the result, and it would just do HTTP range requests from the server or request different HTTP locations to get different chunks of some file. And that works transparently the same way as it would in local code. So I'm not saying that lazy I/O is always a good thing, especially with server round trips, but it's really nice that you can do it. And the JavaScript that I already mentioned. So, well, the GHC pipeline is something I'm coming to in a moment. Just first I can show you a few interesting examples. Okay, this is very dark. Well, many people want to get rid of JavaScript, of course. It's JavaScript is being used for larger and larger projects with lack of support for proper types. It scales fairly poorly in all these callbacks. If you have server requests, or if you have worked with Node.js, then you probably know really well. Every JavaScript is single-threaded, and the way you get around that, trying to do multiple things at once, CPS transforming everything. Everything becomes a callback, and everything gets nested deeper and deeper and deeper. And you can work around that with some things like promises. It's still rather annoying to have to work in that way, since it breaks lots of things you often want to be able to expect from things. If you have some sequential I/O thing, you want to have that as sequential I/O, and exceptions don't work if you have to CPS it. So all these things, they get solved by runtime. But the things I'm personally interested in is that the web is a really great way to show people your results. It's the only way that actually has this great reach. I really like Haskell, and I like explaining things. So I like being able to use Haskell to explain things over the web. So I have a few examples. For example, this year I was a mentor for the Google Summer of Code project from Russia, who's created a page-bin site where you can enter your Haskell code, and you can evaluate it on the server. It gets direct results. It's really nice. It's in the direction of the things that I really want to go and want to extend GHCJS to support better. So one of the examples is something really simple. I prepared for. Yes. So it's really short code. It's some. Is it still too small?
Yeah, sorry, it's a small screen.
The code itself is not terribly important, I have to say. But it just goes to show when you enter some code. I think I'll show another example first because it has graphics. By the way, the URL is paste.hskll.org, so just Haskell without vowels, and I think in Russia they can actually pronounce that if I can't. Let's try to.
Yes. It's there.
Make it a bit smaller. So one of the things that you can do is just run paste. I hope it loads. Yes. So you have some Haskell code, and it renders the result with the diagrams line. This was one of the goals. This is. I'll tell Daniel that he's joking. Well, it's really nice. You should really try it out. You can use it to demonstrate Haskell code, and it's, I hope, more useful than Lambda for doing larger problems. But the second half of the project was using GHCJS to make interactive results. If you have something that's a diagram at the top level, then it will render it, and you can create really nice images. If you have something that's not final value, but well, where it's here. But the function, then it will compile the code that you enter for GHCJS. It's a bit rough at the moment, but we'll work on that. And you get some interactive UI that will evaluate the code for us. So this is just, well, it's a bit small, but it's the Fibonacci series where you where you specify the first two numbers, and then it will take the first 10 elements of that. So that's a function. The basically detects that it's a function, so it lets you enter parameters, and this is one of the parts that's really easy to fix, but it's really easy to fix. I've already written the code for that. So I entered the two parameters, and I think it was 4 and 6, so it starts with those and so and that's really nice. This is all run on the client side. Yes?
Can you show the output in JavaScript?
Well, it's pretty big and pretty hairy, so I'll go to the JavaScript code when I'm explaining what kind of code we generate, and then it will also be a bit easier to understand.
Okay.
So if you want to dig into the actual code, we can discuss that after the talk, I think. Okay, well, this is interesting, but I want to do more. I was working on something similar to what's now called Haskell. But I don't want to just show Haskell things. I want to use Haskell. I like Haskell on the web to show anything at all. So I made another example just with GHCJS. A simple classification algorithm. Say we have some observations, some examples, and we want to make a classifier. So I have some measurements, and I have these measuring points that are blue. Oops, I shouldn't have done that. Everything is blue. And I have some red observations. Like this. So that's you can see it, right? So we want to make a classifier, and this particular kind of classifier that I'm talking about is the support vector machine, and which means we have to draw a line between these two point clouds, and the line has to be at the optimal position to separate them. So you draw a line, and above the line, in this case at least, everything will be blue, and on the other side, everything will be red. Well, where do we draw the line? We could draw it vertically, but then it would go very close to the red and the blue points. So for support vector machines, the optimal line is the line that goes exactly through the middle of the two clouds. And the precise definition for that is that if you have the line, then the area of the space around the line that does not contain any points is maximized as large as possible. So that's a nice, at least in 2 dimensions. Usually these are used in very high dimensional space, but it's a bit harder to draw here. So I use 2 dimensions. So this gives us a nice optimization problem, which you can use, can solve with a fairly complicated algorithm, basically it's not really a hard optimization problem, it's a convex problem. You can iterate through it. It's a constraint optimization problem, so very briefly, you get some, you restate the problem in terms of Lagrange multipliers, and you iterate updating a few of them at a time until you get at the optimal solution. And the interesting thing about this, if I enable this, and there's working in my code, so if anyone wants to help me find it, I hope it does a decent job now. No, this is also the wrong thing. So I said we have a line. This looks decent, but if you look at the actual definition of support vector machines, then you'll know that this still looks a bit off. So there's some threshold probably that I'm calculating wrong. But this runs in the browser, and I really like that you can compile this kind of algorithms, and it runs decently fast. It runs on, I think it even runs on box arrays. And all the box arrays will be much faster. And this is the kind of thing that I really want to show. So we have the sandboxing for Haskell code in the base bit side already, and the JavaScript compiler that can run these things, and I really want to extend it so that we can show more things. And not only teach Haskell with the browser, like school of Haskell, but teach everything with Haskell in the browser. So the nice thing about implementation, it's a fairly hairy algorithm, but compared to Java implementation made 2 years ago or something, the JavaScript code is much closer to the definitions in the paper. It's much nicer to use laziness to not compute things all the time when you don't need them. So I really like to be able to do that. Well, the last thing I'm going to say about this example, because it's a bit of a version, but still I really like it, even though I didn't manage to get it completely correct. I probably shouldn't have started working on it yesterday. So, is that the optimization is when you express it in terms of these Lagrange multipliers, it only uses the inner products of the line, the normal vector of the separating plane, and the measurement points. And the interesting thing is that if you have normal inner product, just normally taking space inner products, then you get these kind of lines, but you can make more fancy inner products that square the inner product or do a higher degree, or even use an exponential function. So that was one of the things that I accidentally set it on. So if we switch to a Gaussian function that has an exponent, it will implicitly project all my measurements to a higher dimensional feature space. You can, well, this one is a bit hard, but at least the polynomial one, it's this one. You can multiply it out and you can see that it will have some, have computed implicitly some inner product for a higher dimensional space that has all these cross terms between the, in this case, the y and the x direction. So I think it's really nice that you can show in the browser, have immediate response. I haven't optimized it at all. I should identify the B parameter, which is the degree of my polynomial kernel. So well, this one is clearly a bit worse because it misclassifies two of my measurements. But I really like to be able to do this kind of thing, and I hope that there will be more things following. So some basic infrastructure, running Haskell code on the internet, and having lots of interactivity and things to play with are fun. But now on the boring part, since before you can play with this, we have to start from Haskell, have all these translation layers, and well, that's going to be probably the rest of the first half of the talk. So GHC, like all compilers, have lots of intermediate steps. Well, not that many actually, so much people with 50, but this is a decent number. So we start from Haskell, and that gets parsed. And type checking and desugaring, sorry, not desugaring, type checking and renaming. Renaming means resolving all names to where they come from, which package, which module, where they're defined. So you get the types and renaming in one go. Is done on the Haskell source code or an abstract syntax tree of that. Then it's desugared, where, for example, the monads do syntax, etc., is all removed, and everything is converted to a very simple functional language, and that's the one that's used where most of the optimizations that GHC does are performed on. It's when you have rules in your Haskell code, the rule parameter, then you will apply some rule rewrites to the intermediate core syntax. After doing the optimization and all the other simplification steps on core, it will translate into STG, which stands for Spineless Stateless G Machine. It's both an intermediate language and an abstract machine for running Haskell. But it's basically looks very much like core. It's a bit more complicated, but it has a bit more data available that we use in GHCJS to generate upload from. It's the form that the code in is a bit stricter, so which makes it easier to generate code from. Well, normally GHC would then go on to run the code generator in general, and it would generate CMM. CMM, or C minus, is a cross-platform assembly language. It's somewhat high level. It looks a bit like C, but well, it's not really meant by it's not quite the same as C. C is actually not a great target to compile Haskell to. And normally the code generator would either be the native code generator and generate the native code directly through assembly language, or it would output LLVM bit code and use the LLVM optimizer to generate the final code. But the problem is CMM is already fairly low level, and if you want to translate to a high level language like JavaScript, we have lost lots of information about Haskell. So I briefly looked into it last year. People ask questions every year, why don't you do that? And there are many interesting projects going on in this area. SNGS, Firefox, for example, is loaded up JavaScript at the LLVM level, basically, for really fast combination of a specific subset of JavaScript. And it might be used doable to translate LLVM. There is a compiler from LLVM to SNGS available, but the problem is it's much harder to nicely integrate Haskell with the rest of the browser if you go through this really low level. So instead, we did make the choice of using STG as our source language. But first I'll explain a bit more about these steps. So Haskell, like I said, the parser and the type checker run on that. It might be easier to do renaming and type checking on an intermediate syntax like core, but it would make error messages much worse. So we choose to do it on the rather complex Haskell obviously directly, and that's a lot more user friendly. Unfortunately, we don't have to deal with it. Core is, it's based on System F. It's an extended version. It has been extended a few times. It's System FC now, but it's more or less a polymorphic lambda calculus. If you have to inspect the core output, I think you can debug core, debug simple or something from GHC. You can do that. It's quite fun and probably quite interesting if you are interested in how Haskell is compiled. But it's it's polymorphic lambda calculus. You can see all these type applications, all things going on. For example, if you have a factorial function, pattern matching is about the core is distributed out to just case matching. Pattern matching doesn't exist anymore. If we have something a bit more complicated, like a polymorphic function like map, then you have type variables in the map function. Haskell, you don't see them. Only see the type signature. In the core languages, you get explicit type application. The nice thing about that is that you have all these rebuttals. You can have much stronger guarantees by keeping track of all of these things explicitly, so that you never make any mistakes. And there are a few more things. Everything that's some pattern match or some guard gets distributed out to some case things, so we don't have those anymore. Type class will also distribute out. So if you have a type class constraint for something, here my function is a monomorphic function, but the square root function and the square function, the multiply function is a polymorphic thing, a type class function from the none thing. So whenever you use any of these constraints, core will add extra arguments that are the dictionaries, just data structures containing all functions inside the type class. It will pass them in for us, and it will do all the work. So in GHCJS, since we translate them from after core, we get all of this for free. Then we come to I/O. I/O feels a bit magic, but in the GHC implementation, it's basically it looks a bit ugly and my spacing is a bit off. But if you know the state monet, which is every action in the state monet is a function from a state to some result in a new state. So the I/O in GHC is implemented exactly the same way. You have a state real world, and you generate the code that's represented by nothing, so it's nicely optimized out. And you get an unbox tuple, which also has zero overhead of a new state real world and some result. And in this case, my I/O action is just a unit, so my result is unit. And I/O is implemented as a new type of this weird thing, which means core has some machinery to make sure that this new type maps to the right thing, which is called coercion. These are all used to guarantee the consistency of all the optimization and all the rewrite passes. But we don't have to worry about that very much. So after we've done all the optimization on core, we get the spineless status G-machine code, where we have some nice guarantees. Like, for example, GHC has lots of primitive operations, primops, which are the low-level things that you can't express in Haskell directly. So we do foundation support. You know the arity for these things, you know how many arguments they get. So it's easy to make sure that everything every of these things is fully saturated. So you never have a partial application of some primitive operation. That makes it really easy to generate code for primitive operation called data. Also for data constructors, you know how many things fit inside a just constructor, for example, one, and a cons constructor two. And those things you have to have constructor that do this no polymorphism is happening at all at this point. So these are all fully saturated. A normal form is also kind of useful. It's independent now. And the other thing that GHC has done for us is annotate the whole AST, tracking all dependencies of every expression. So if some expression has a free variable, if you do a pattern match, it will tell you what variables it depends on during the pattern match and which variables it depends on in the case statements, all these switch things after the pattern match. And that's really nice because we really need that in GHCJS. So that's SDG is where we start from. Well, this is the part of the pipeline that we add. GHCJS is all in the GHCJS package, we translate SDG to JMacro. JMacro is an EDSL for generating JavaScript code. It's my Gershon. It's pretty nice. It's a simplified JavaScript AST, and it allows us to do lots of analysis on the code. But we don't just start from SDG, since I mentioned we have this special JavaScript for a function interface, which means users can enter their own JavaScript code inline in Haskell. We have this pattern placeholder syntax that I'll explain in a moment. So all the foreign imports that use this, they also get added to our SDG. So we parse those and we splice them in. And then we have a whole bunch of JMacro code. And, well, it's kind of hard to generate proper, nice JavaScript in one go from SDG, from Haskell. We could make the code generator really complicated, but like I said, we have a concurrent runtime at the moment, and I'm porting our non-concurrent runtime from the old generation to the new one. And if we have all these low-level optimizations in the code generator directly, it would be really hard to make it modular in a nice way. So instead of trying to output the shortest, best, nicest to read JavaScript code or JMacro code in one go, we have an optimizer that rewrites the JMacro AST and then to give us the final code. Well, it turned out that optimizing the JMacro AST, the analysis on that is rather annoying. Normally, if you do optimization, then you work on some specialized data structures, and it turned out that doing some more or less general purpose AST was not really going to cut it. So we have an internal format that's some kind of graph that we do optimizations on. Then we translate back to JMacro. And if you compile a single module, then we stop there. Yes?
5 minutes.
Yes. So where GHC for native code would generate an object file, a binary file, we generate a JS object file, which is a serialized AST with all kinds of dependencies in between. And all metadata. First we used a text-based format, but it's really hard to scale to binary files. So we have intermediate binary files, and when you link an executable, what exactly that means at the moment, then you preprint everything to the final JavaScript if you can run in the browser online. So that's our pipeline of 2 classes, but it's very straightforward. JMacro, like I said, EDSL for JavaScript. It contains a JavaScript parser, or somewhat extended JavaScript syntax, which we use for our function interface. and it has a quasi-quoter that you can use inside your Haskell source code to enter some JavaScript, and we use that extensively for implementing our primitive operations and many other things of the code generator. So a small example like this, can everyone read this? I hope so. Well, you can make a function of x and y, and the backticks there will anti-quote out of our JavaScript environment and into Haskell again. So I can call their Haskell function that will result in some JavaScript expression, and that will be inserted at that point in the AST. And you can make quite a nice modular JavaScript code. We generate lots of our runtime system with that. We have lots of repetitive parts in the runtime system, and the code generator is also has these places. So that's very nice. So to use it in two places. When we generate code, there are a few things that are important. Like I said, we start from SVG, which is a very simple language, and the only things that are actually still important here are the primitive operations, the things that we couldn't implement in Haskell. Let and case, which are let means allocating new things at this level, and case means pattern matching on something, so I'll probably force it. And for an imports, so those are the things that really matter for code generation. Well, let's start with the primitive operations first. I have a few examples here. GHC has lots of primitive operations built in, and we implement most of them in GHCJS. A few that are optional to implement, like the new vector instructions, we can't implement them in JavaScript, or at least we wouldn't gain any benefit from them because JavaScript does not have vector. JavaScript does not have any support for vector things yet, so we don't have them, but at least we have most of the other things. So and we implement them with JMacro, and if your Haskell code compiles down to some low-level primitive operation, eventually everything will, then this will just be code that splices in. So the first one is double GTO, so just comparing two double precision numbers, and we can compare them with JavaScript, well, one of the annoying things of some changes in GHC 7.8 is that all the comparison operations are now returning, instead of booleans, they return integers, 0 or 1. It feels a bit wrong in JavaScript, and it is. Especially as we'll see later that Haskell booleans are actually compiled to JavaScript booleans. So here we want a boolean usually, but we get a number out of it, and that's where our optimizer comes in here and eventually optimize out nicely. So we have, I think, 200 or so of these primitive operations, well, they are all mostly implemented this way. Some of them are kind of hard to inline or just too long. So, for example, for our MVar, so concurrency for STM, yes. Do you have a question?
Just about one of the primitives. Like, he swapped 16 off. Is that something that someone programming Haskell would regularly use? Or is that to translate the compiler would generate?
So that's what Johan Tibble uses to make unordered. That's one of the things he wants for unordered containers. So it's you're doing some shuffling hash.
You can take this offline.
Yeah.
Well, if you want to finish up at 10.
Yes, I will discuss the rest of the things later. It's just also. Okay, where were we? Generating code. So the primops, pretty straightforward. Is it working well?
Sorry. Just give it a second.
Okay, it's to show the primops, the one that you've already seen and contains nothing new. So let's switch to the next one. Yeah. Okay. So the next thing is for an import. Like I said, we have like Fay and GHCJS. The interesting new form JavaScript MVar extension. It's enabled, or it's included in GHC 7.8, but it will always give you an error unless you use JavaScript code generator like GHCJS. So with the native compiler, you can use it. We'll see what's annoying. How many seconds does it take? Yeah, should I? Oh, it's my screen here also went off. Okay, it's back here. So that. No, then. Oh, this is really the start part of the whole part. Yeah, I also can't show you the examples. So, what's the plugin?
Yeah.
Can you do that?
There we go.
Oh, yeah.
See, I'm the computer whisperer.
Great. So, this is what our foreign syntax looks like. We support foreign import SQL, like everyone uses at the moment, because it's the only thing. Well, there are a few more, but they do basically the same variations on. All the things like pointers, etc., they are supported through some calling convention. So obviously JavaScript does not have pointers, but it does have type arrays, and it does have it has numbers. So for example, pointer is just a type array and an int. They don't get boxed into objects. We really try to avoid wrapping things in objects as much as possible, because memory allocation is rather expensive in JavaScript, much more expensive than in GHC runtime. So we have a calling convention, and you can implement any SQL import from existing packages in JavaScript and make the package work. Sometimes you might need to implement a large library, but in many cases just something small, and it's really easy to make it work. But the JavaScript for the imports are the interesting ones. We have the basic flavor is that you have some inline JavaScript code that gets spliced directly into the function. You're not limited to single expressions. You can use any JavaScript statement there is. It will rename any variable you need there or whatever, so it doesn't clash with any existing thing. So in that respect, it should be type safe. Normal foreign imports are safe foreign imports, and the safety specifiers are. We take some liberty with that, but they have a fairly they mean something different than in the native platform. So if you have a JavaScript import and it's safe, this is the default, like the math syn thing, then if there's JavaScript exceptions thrown in the JavaScript function, then it gets called by the foreign function caller and it gets rethrown as a Haskell exception. So you can catch it as a Haskell, it's wrapped in a JS exception. You can extract the original exception out if you want, or you can also just convert it to a string. So you can just catch that in your Haskell code and it works like expected. Unsafe imports don't catch the JavaScript exceptions, so you get a bit shorter code and maybe a bit faster. But if you then get a JavaScript exception, then your Haskell thread, not all Haskell program, all the 4.0 threads run separately through our scheduler, and just a thread that receives one exception. The interesting one, or the most interesting one, is the interruptible ones. And these are, like the name says, actually interruptible. And these can be used for asynchronous JavaScript calls. So the jQuery library is quite a common JavaScript library for doing DOM manipulation, also doing server calls, like this Ajax call. If we import it like this, and it looks like my multi-line strings got messed up a bit by LHS tag, but this should be a multi-line string with backslashes, etc. If you have an interruptible import, then it becomes interruptible, which means you can throw an asynchronous exception to that thing from another thread, which aborts the call. But what the interesting thing is that you don't return a result immediately, like you do with the other function foreign calls, but you get a special placeholder $C, which is a continuation. And when you call the continuation, then you return the result to the Haskell code. So from the Haskell code, like you can see in the type of this thing, the JS string, which is just a Haskell wrapper around the JavaScript string, and the JS wrap, which is a polymorphic JavaScript object wrapper, to an I/O that gives some JS wrap of an object result. So it just looks like a regular I/O action. So in the runtime, this suspends the current thread. It jumps to the foreign code, and when you call the continuation, it it wakes up the thread again and it runs it with the result. So you can have, at any point in your code, you can have this kind of asynchronous things. So if you have unsafe interleave IO, for example, you can have pure code, things that are pure but have these asynchronous things in between. So you can, in a really easy sense, transparently request things from the server or request user interface and just work in the easy, nice, step-by-step synchronous way. And JavaScript, for JavaScript, it just looks like any other asynchronous code. So you don't block anything in the JavaScript runtime with that. So and exceptions, like I said, they work as expected. So this makes it a lot easier to program more complicated systems. Well, other than just the extension, we have made a few changes in the FFI. For example, the C-call FFI, when you pass a boolean to get to some foreign function, it gets converted to 0 or 1, which is not in JavaScript because we have real booleans there. So types have changed a little bit. Well, the C-call FFI doesn't really have something that maps well to JavaScript objects. We want to integrate with JavaScript very well. So, for example, if you want to pass around some arbitrary JavaScript object or a function or whatever, we need something for it. So we added sometimes, and one of the changes that recently got merged into GHC 7.8 is the ability for libraries for users of the GHC library to actually modify these things. So this is just a start. I've only done the really important basic things, but more things can come. And these are the safety things that I explained. Well, if you ask me one thing that would be, tell me one thing that's different from the older GHCJS that we basically spread to rewrite it to make something that works a bit better. To the new version is then that would be the way we do closure conversion. Most Haskell to JS compilers, there are a few, they compile Haskell closures to JavaScript Haskell closures. That makes sense for, but we ran into some trouble with it. In particular with the concurrent runtime, it's really hard to scale it very well. And since we have all the information from the GHC API about free variables, dependencies, and expressions, we can use that to do our own closure conversion. And I measured this, and to my surprise, it's not really slower, and in some cases it was even faster than using JavaScript closures for this, and it has a few additional advantages to really do Haskell correctly for at least larger scale programs. So the simple thing that we can do, that Faye, for example, does, if you have a function, this function that compares to integers, I'm not going into curry yet, I'll talk about it in a moment, but it is a function g of x and y, and it does two pattern matches and then reduces back to some primitive, the spacing messed up a bit, but it should be the greater hash. The hash sign is often used for primitive operations. So it reduces two integers which have an I constructor and some primitive integer inside, and then compares the two primitive integers inside the primitive operation and then gives back a bool. So that's a very basic function. Well, Faye does something like this. It has to force two values, so it calls some function to reduce that to weak hat number form. So it gets back the constructor, and then it can get the fields out to do the actual comparison, the primitive comparison, is just the JavaScript comparison in this thing. Well, this does not give you concurrency, because you call into something to reduce something. And the problem is when you recurse on the JavaScript stack, you can't jump out of some recursion to switch to another thread or do all the lazy, interesting asynchronous form function defense things that I mentioned before. So, well, we can't use it. So our first version used something like this. It looks a bit hairier, but it's basically the CPS transform version of the first one. We still use the JavaScript closures to capture all the variables. but instead of calling something, we return something that has a function that will be called for our next result. So in this way, since we don't use the JavaScript stack to recurse, we can easily switch threads. But the problem is, you can see already here that, well, we have 4 functions here. 3 of them are local functions. They are JavaScript closures and local closures. So they have some context that needs to be allocated. And this really scales very poorly. So this is not a great way to go about this, although it works. But, well, it has some other limitations. So our new GHCJS version basically does this. This is more or less what GHC code for the native code does. Instead of nesting all our functions, we only have top-level functions, and we use a stack in the JavaScript array. Haskell stacks in the native runtime are these dynamically growing things, so you can support hundreds or thousands or hundreds of thousands of lightweight threads. And, well, the nice thing about JavaScript arrays is that we also dynamically grow. So we have, for every thread, we have a thread state object which contains a stack and some other thread state things. And when we recurse, when we call into something, we push something on the stack, which is our continuation. And when we reduce something to weak and normal form, it will jump back to what we have on the stack, and then we can continue our computation. So instead of using JavaScript closures, we manage everything ourselves and use all the GHC information to push all the things that we need on the other side of our pattern match to the stack. So this is a bit more work. This code looks really long, but if we run our optimizer on this, it's actually not that bad. And if you test the performance, then it's almost as good, almost as fast as the direct calls in many cases. And in all cases, it's much faster than the CPS transformed manipulating things. And there's another thing that's really important for larger systems. And that's the topic of after currying. So far I haven't discussed currying yet. The functions I've shown are just things of one argument. And you can of course easily, like I said here, convert function of 2 parameters to something like this, return new functions and only use function of 1 parameter. But that would introduce all these local closures again. And like I said, we try to avoid memory allocation as much as possible, since, well, especially Firefox has a terrible garbage collector, and Chrome does a bit better, but they are not as good as GHC itself. So, well, we want to do currying in a more efficient way. GHC in native code already does that, so we just copy this trick. But we have a few different situations here. For example, if you have a map function, you get a higher order function, you can pass in function f. You have no idea what arity that function is. We have a function from A to B, but maybe B is another function. So map, if you use some if you map use the map function, it doesn't really know very much about the function f at all at compile time, because you generate code at compile time from f without knowing the f. It's polymorphic. Well, in other situations, it is functions are known. Like here, the twice thing that just appends a list to itself. It uses the list append function, and that's just a thing that you know. It is a polymorphic thing, but you know at least the arity of the thing. It takes 2 arguments. And also from the type, you can't see the arity of a function. The first f1 function is an arity 1 function that returns a lambda, and that's a different beast than the f2 function. It's actually an arity 2 function. So we have at runtime many situations where we don't know the arity, where we can't hard compile the arity in. So we have to do some work to make currying fast and make it work correctly. So, like I said, currying, you can do it by currying everything in a more efficient way. We can do the trick that GHC native code does, which is called eval apply. If you want to call some function, you apply the function, then you have to evaluate it first. The function might be a blunt, it might still require some computation before you actually get to the function. And then you apply it, then when you have a function, you have at runtime some metadata where you can see if you have, when you do a function call, the right number of arguments so that you can jump to the function. So at runtime we have some metadata, and we then try to apply the function to the right number of arguments directly without all these intermediate steps. In most cases, we can use more information. We have non-function calls, so we can optimize the runtime parity checks out. And if we don't, then we have to go through some runtime checks. And depending on whether we have exactly the right number, we just jump to the function. If we don't have enough arguments, we create a partial application. And we have too many arguments, then we have some leftover things. Our function application would return another function, like I showed with the lambda. Then it would push the other arguments on the stack, and it would automatically apply those again. We do second application when the first computation returns. So that's basically what native GHC does, and it works pretty well for us since we have the stack and everything in place. Well, we have in Haskell many types. Most of the things. Well, I think I should have. Sorry. Most things, when we have a stack, we do our own closure conversion, which means that Haskell closures look like JavaScript objects. You just have some properties, but with some fields that we can look up. Those are contain all the variables. All the free variables, we can look into them, which is a huge advantage. JavaScript closures, you can't look into them, and those will bring a pretty big problem. I'll come to that in a moment. But GHC has lots of primitive types and also a number of types where we can do some special things. So all these word hash, in64 hash, etc. These can be converted to low-level JavaScript types. So word64 is converted to two JavaScript variables that are both a number. They are not wrapped in an object, so you can do efficient 64-bit computations, never wrapping intermediate results in objects, which makes it a lot faster than having numbers, objects everywhere in between. So some things are size 2, and you have to deal with that when you deal for a function interface. But other than that, from Haskell, it just looks normal. Well, some things are a bit special, like the big numbers. And if we have, that's one optimization that we can make, because JavaScript has this type of operator and a few other things that we can use for some runtime type information. If I have a data type that has one constructor and one field that fits in one JavaScript variable, then you can unbox all values of that thing. So all booleans are just compiled to booleans. That saves a lot of boxing and unboxing. With all integer values, if they're a thunk, then they have to be an object, of course. But if they're just a value, you return an integer, you just return a JavaScript number without doing any application. So that's the list here, and that works for all things that have one constructor and fit in one JavaScript variable. So the generated code looks a bit, that comes out of our code generator, looks a bit like this. So we have a function, and the function, since we do tilde optimizations, we can't do calling functions. We have a main loop that calls the next function every time we return the next function to call to the main loop, and then the main loop calls that function and stores the result, calls it again, etc. So from the main loop we do all the threading, of course, well, that makes it of course a bit hard to, we can't use the regular JavaScript function call arguments, so we use global variables to pass arguments, which is in this case the $r1 thing is the first argument, and that has lots of properties, and in most cases $r1 is the current closure, and all the things that are copied to local variables here are the free variables from the closure. Then we do apparently, then we do call $h$bh, which is black hole, this thing. GHC, when it enters a tongue, it does black holing. It means the moment you start computing something, you get rid of all the things it references. And well, we do the same thing here with GHC. It has its own garbage collector. It's with some memory management, so it can postpone black holding things to before garbage collecting. With GHCJS we have to do eager black holding to get rid of all references to avoid memory leaks during long computations as early as possible. So $80 resets all our references that we just have copied to our local things and we'll use the rest of this function. And then we do some pattern matching, all these the J equality things, some primitive operation that generated this, and then something different converted that thing back into a Boolean. This is pretty bad, all these local copying things, but that's just to keep the initial code generator quite simple. So GHC itself has, after it generates CMM, some optimization passes over CMM using standard data flow analysis techniques. We have similar things but specialized for the JMacro code for GHCJS to make the code a lot better and a lot shorter. We use liveness analysis, constant and value propagation to read out many intermediate assignments and use some runtime system knowledge to know which kind of function we can safely move around. So we can make some optimizations that existing JavaScript optimizers like closure compiler can't do. And we don't try to completely minify the codes. At first, still external optimizers and minifiers are better for that, but we at least try to make the steps to do the things that they can't. So, like I said, this intermediate assignments, etc., are pretty bad. And the optimization doesn't really work very well on an AST type. So we converted to some control flow graph that still has knowledge of our JavaScript structured control flow. If you do regular control flow, data flow analysis, then you usually work on some low-level graph of basic blocks that contain no control flow internally, but optimizing these basic blocks without any reference to JavaScript AST, and then trying to convert it back to some readable JavaScript that's fairly decent in size again. That's just a horrible task. So we have to keep track of many JavaScript things. But at least it's fairly effective. It's the most annoying part of the compiler, I have to say, and currently also the slowest, probably because I use lens way too much. It's so easy to just recursion to something, keep track of all the dependencies of some expression, but then especially the lenses that I use, they depend on some generic traversals and they tend to get slow. So I probably have to rewrite a few before I make the final release in a few weeks. But well, that's a fairly necessary pass, but it works. And well, I wouldn't recommend starting with this if you want to have help on the GHC compiler. So, like we've seen, we do our own closure conversion, which means everything is JavaScript objects. And we do black holding, which means we just reset some references. We do that, at least we try to do that in a way that doesn't fall into the same problems as, I think, Faye doesn't do this, for example. And we try to, since everything is JavaScript objects, we try to rely on the GHC, on the JavaScript garbage collector as much as possible, just reuse the infrastructure. But there are some problems which the JavaScript garbage collector cannot help us with. For example, if you have a global CAF, constant applicative form, like the first one, a list of Fibonacci numbers. Second example, I've used this in. This is a thing that will have a global reference in the global scope. So if you calculate somewhere the 10,000th Fibonacci number, then it will, for the rest of the duration of your program, it will keep that list in memory. GHC in native code keeps track of all static references. It will know when you're no longer using some global data thing. But JavaScript, of course, it doesn't know anything about what we're doing with global data. Well, there are some other things where it might not be as apparent, but it's still happening. Like here, say you have a hash table with internal addressing, and you want to calculate the table size for n elements, the minimum table size, and it has to be a prime number. So if you have some global, some local prime number list here, GHC will find out that primes does not depend on any of the arguments of table size.
just a static list. So it will float down to the top level, and, which is in some ways nice. It improves sharing. You won't have to recompute it all the time. That means you have more global data that JavaScript will have no idea to deallocate. And well, this can get pretty big. But fortunately, since we do our own closure conversion, we can inspect every object that we have currently running in our Haskell runtime. So we can do something about that. We have a heap scanner. Unfortunately, it does not have to run as often as the JavaScript garbage collector. That still does almost all of the work. But say you have a large, long-running application, then our inspectable heap allows us to scan everything that's on it and just decide what's reachable, what's not, and we can reset global things to something that can recompute them again. We can, for example, also run finalizers for read references, well, like I said, we use JavaScript dynamically growing arrays, and these might grow very large, and then we retreat to some decent level. So we also use this for making sure that these don't use too much memory. So for larger, long-running programs, that's pretty useful. I think we're the only one doing that. I hope that this makes it more correct. But there is some problem. Of course, when you interact with foreign JavaScript, there is some API from the runtime that might start new things again, and there may be references from event handlers or something that are not currently scheduled by any threads in the runtime. So we have to keep track of some extra information ourselves to make sure that we don't clean up too many of these things. And well, there are some trade-offs that can be made, and you can basically tune this for your application. But usually for large applications, when you have some large-scale rescheduling or restructuring or something, you might run this scanner one time and make sure that it gets rid of lots of data that you might not be interested in anymore. And if in the lucky event that you still need to recompute something, it will still be available. In case of unsafe perform I/O, where you really don't want it to be reset, you can keep track of that, but I haven't really implemented it yet. So you can do that in a safe way so that you have a guarantee that even if you add more new Haskell threads from JavaScript, will never result in some I/O action being performed multiple times. So, this is all the code generation. After you have all the code, sorry, I have to be a bit fast, so we'll do that after the talk. We link everything. Basically, we implement split objects. We keep track of all the dependencies of every symbol, and we generate a huge bunch, very big chunk of JavaScript that only contains the things that are reachable from some main module, and it also generates some extra files that are that you might be interested in for making your own deployment work. There is some API where you can start Haskell threads, run I/O actions from JavaScript. Mostly the easiest thing is just to run the main I/O action and use all the GHCJS base library to install all your user interface and make all the callbacks from the Haskell side. But you can also do it from JavaScript. Well, there is still work to do, but and that's mostly to do with system-specific tools, but that's kind of boring, I think. We have to deal with configure scripts and doing, for example, HSC2HS runs the C compiler, and that won't really work if you do JavaScript, but still it's possible. It would be nice to support things, to support packages that rely on that, so we will have to do some work to make it really usable. But there's one really cool thing that I really like about our closure conversion. Since we can inspect the heap, we know exactly what's going on. We have our own thread scheduler, so every reduction is performed in some main loop. We can, so at every point of some reduction, we can stop everything. We can scan what's going on. And well, this is some example that I made a few months ago, and it's running very old GHCJS code. But this runs the expression that, well, it's in there. The blue things there are the stack, and it's just running one computation step at a time. You don't really have to read it, but it's a fold L and not a fold L prime. And you all know this will eventually cause a stack overflow, but not before it first builds up on the heap a large chunk that's still it's not being forced. So it just keeps building it, and after it has built the whole chunk, it's only this from 1 to 10. It's pushed everything to the stack. Well, it doesn't fit on the screen, so it's not a stack overflow yet, but if it were big enough, then it would have been. And you can also run this one. And this is just the GHCJS runtime. This is a weekend project. I did it in two nights, and it just stops the whole computation every step. It makes a graph using an existing JavaScript graph drawing layout library, and it's then does the next step. So
Zoom in a bit more?
Command plus.
Command plus. I hope it works.
Yeah, great. There we go. A little bit. Yeah.
There, perfect.
So you don't really. The blue thing is just a stack, which is really the stack that GHC uses. It uses the same kind of stack. So this can, if anyone is interested in expanding this, we have the sandbox runtime that I showed before for the base bin. I'd really be interested in expanding this for showing Haskell, making a user interface for stacking through the evaluation, and allowing users to enter their own expressions so that they can get compiled with GHCJS, and that they just see what's happening and what's really happening. Since this is not only what GHCJS uses, GHCJS uses only almost the same runtime system as GHC, so stack usage will be the same. So if we have full R, then it will, well, this is a lens thing that's really a chaotic thing. But it's, lens does weird things and I'm not sure how this looks. Well, okay, I think I have to wrap up. So thank you for your attention, and I hope everyone will try GHCJS when it's
Thanks, Luite. If you have any questions about this, you should join us at the bar. We don't really have any questions right now, but Luite will be there. You can buy him a drink, and he'll tell you as much as you want to know about it.
Maybe more.
What bar is that?
Which bar is that?
Central City Bar?
We're going to have an announcement at the very end, and there will also, of course, be a crowd heading there that you can follow.